Have you ever wondered about the concept of infinity? Can you truly grasp how endless it is? Let's take a moment to dive deep into the realm of the infinite. Infinity, a term so familiar yet so elusive. It's a concept that's been pondered and debated by great thinkers for thousands of years. The ancient Greeks, for instance, had a word for it, apeiron, meaning boundless or unlimited. But it wasn't until the late 19th century that mathematicians like Georg Cantor started to formalize this concept in the field of mathematics. So, what is infinity? Well, it's not a number in the traditional sense. Instead, it's a concept that represents something without any bound, something that goes on forever. It's the idea of an unending quantity or series. When we say something is infinite, we mean that no matter how much we count or measure, we can never reach an end. In mathematics, infinity is used to describe quantities that are larger than any finite number. It's the idea that there's always a bigger number, no matter how large a number you can think of. It's used in equations, in calculus, and in many other areas of math. But infinity is not just about being big, it's also about being small. In the world of fractions, for instance, you can keep dividing a number by 2 and you'll never reach 0. You'll just keep getting smaller and smaller fractions. That's another kind of infinity. Infinity also shows up in geometry, in the concept of a point at infinity. This is the idea that parallel lines, while never meeting in finite space, do meet at an infinite distance. The concept of infinity challenges our understanding of the universe and our place in it. It's a concept that pushes the boundaries of our thinking, forcing us to grapple with ideas that are beyond our everyday experience. Infinity is a fascinating concept, but did you know it comes in different sizes? Sounds strange, right? Well, sit tight, as we're about to explore the intriguing world of countable and uncountable infinities. So let's continue our journey into the infinite. Imagine a never-ending line of dominoes. You could count them one by one, and you'd never reach the end. That's an example of countable infinity. To understand this concept, picture a vast, unending sea of numbers. Starting at 1, you can count upwards 2, 3, 4, and so on into infinity. You might grow old and weary, but theoretically, you could continue counting forever. This is the essence of countable infinity. It's infinite, but you can list each element in a sequence, one after another. Think of your favorite book. Even if it's as thick as War and Peace, it still has a countable number of words. Now imagine a book that never ends, with an infinite number of words. It's overwhelming, isn't it? But here's the catch. Even though there's an infinite number of words, you could still list them one by one. That's another instance of countable infinity. Now, let's delve a little deeper into the mathematics of it all. The concept of countable infinity is closely linked to something called one-to-one correspondence. Picture a long row of chairs, each with a person seated. If we can pair each person with a unique chair, we say there's a one-to-one correspondence between the people and the chairs. Similarly, in a countable infinity, each element can be matched with a unique natural number. There's a one-to-one correspondence. So, in our never-ending line of dominoes, each domino can be paired with a unique natural number. The first domino with 1, the second with 2, and so on. Even though there are infinitely many dominoes, we can still list them out one by one. Countable infinity, therefore, is like an infinite list. It's a concept that challenges our intuition, but it's a cornerstone of modern mathematics. It's the infinity that we can, in theory, get our arms around, one element at a time. So, countable infinity is an infinity you can list or count. But what about infinities that you can't count? Now consider all the points between 0 and 1 on a number line. Can you count them all? There lies the concept of uncountable infinity. Imagine trying to list all the numbers between 0 and 1. You'll quickly realize it's an impossible task. No matter how many numbers you list, there will always be more. This is because the number of points between 0 and 1 is not countably infinite. It's uncountably infinite. When dealing with countable infinity, we can establish a one-to-one correspondence. For instance, we can pair every natural number with its double, and we won't run out of pairs. But when it comes to uncountable infinity, things get a bit trickier. Consider trying to pair each point between 0 and 1 with a natural number. You might start with 1 paired with 0.1, 2 with 0.2, and so on. But what about 0.11 or 0.12? You'd quickly find that there's no way to pair every point between 0 and 1 with a natural number. There's simply too many of them. This is what we mean when we say that the set of points between 0 and 1 is uncountably infinite. Now you might be thinking, but infinity is infinity, right? How can one be larger than the other? Well, that's the beauty of it. When dealing with infinity, our intuitive understanding of size and quantity can get a bit fuzzy. Countable infinity is the size of the set of natural numbers, while uncountable infinity is the size of the set of points between 0 and 1. Even though both are infinite, there are clearly more points between 0 and 1 than there are natural numbers. The concept of uncountable infinity challenges our understanding of size and quantity. It forces us to think outside the box and consider that maybe, just maybe, not all infinities are created equal. Uncountable infinity is larger than countable infinity. Hard to believe, isn't it? Ever heard of a hotel that's always full, yet always has room for more? Welcome to Hilberts Hotel. Imagine a hotel with an infinite number of rooms, all of them occupied. This is what mathematician David Hilbert proposed in the early 20th century. Now, suppose a new guest arrives. A regular hotel would have to turn them away, but not Hilbert's Hotel. It simply asks every guest to move to the room number next to theirs. So the guest in room 1 moves to room 2, the guest in room 2 moves to room 3, and so on. This leaves room 1 empty for the new guest. And voila! The hotel is still full, but it accommodated the new guest. But wait, it gets even stranger. What if a bus arrives with an infinite number of new guests? Again, Hilbert's Hotel has a solution. It asks every guest to move to the room number that is twice their current one. So the guest in room 1 moves to room 2, the guest in room 2 moves to room 4, and so on. This leaves all the odd-numbered rooms empty for the new guests. Once again, the hotel is still full, but it has made room for an infinite number of new guests. Hilbert's Hotel serves as a fantastic illustration of the strange and counterintuitive properties of countable infinity. This concept shows us that in the world of infinite sets, the whole can be the same size as some of its parts, and that adding more doesn't necessarily mean getting more. It reveals that infinity is not a conventional number, but a concept that stretches our understanding of mathematics to its limits. So the next time you think about infinity, remember Hilbert's Hotel. It's a place where the impossible becomes possible, and where the rules of the finite world no longer apply. In the realm of infinity, adding more doesn't always mean getting more. Scene script. How can we prove that some infinities are larger than others? Enter the diagonal argument. The diagonal argument is a beautifully simple yet powerful tool, devised by the mathematician Georg Cantor in the late 19th century. It provides the proof that there are indeed larger and smaller infinities, countable and uncountable. Imagine you have a list of all possible decimal numbers between 0 and 1. Every number you can think of is there, sorted in some order. Now let's construct a new number that's different from every number on that list. Here's how we do it. We'll go down the list, and for the first number, we'll change the first decimal place. For the second number, we'll change the second decimal place, and so on. We'll make sure that the decimal place we change is always different from the original. This ensures that our new number is different from every single number on our list. But wait a minute, this new number we've created, it's also a decimal number between 0 and 1, right? So it should be on our list. But it can't be, because we've made sure it's different from every number on the list. This is a contradiction, and it means our original assumption that we could list all decimal numbers between 0 and 1 must be wrong. This paradox is the crux of the diagonal argument. It shows that the set of decimal numbers between 0 and 1, also known as the real numbers, is uncountable. There are simply too many of them to list. In contrast, the set of natural numbers, 1, 2, 3, and so on, is countable. We can list them. So, contrary to our everyday intuition, there are different sizes of infinity. There's a larger infinity of real numbers between 0 and 1 than there are natural numbers. The diagonal argument gives us a glimpse into this fascinating world of different infinities. So, the diagonal argument shows us that not all infinities are created equal. Infinity is not just a mathematical curiosity. It has profound implications in various fields. Consider physics, where infinity plays a pivotal role in theories describing the universe. In cosmology, for instance, the concept of an infinite universe has been a subject of debate for centuries. If the universe is indeed infinite, it implies an endless expanse of stars, galaxies, and perhaps even multiple versions of you and me, existing somewhere in the cosmic vastness. Moving on to philosophy, infinity stirs up thought-provoking questions about the nature of reality. The notion of an infinite past, for instance, raises the philosophical conundrum of how we ever arrived at today. If there were an infinite number of days before today, wouldn't it take an infinite amount of time to reach now? Yet here we are, existing in the present moment. Now, let's talk computer science. Infinity is integral to the study of algorithms and data structures. For example, programmers often use the idea of infinity as a placeholder value in algorithms, especially when they're trying to find the shortest path between 2 points in a network. Using infinity as an initial value allows for any real distance to be shorter, thus facilitating the process of finding the minimum. Infinity also impacts the theoretical limits of computation. The concept of a Turing machine, a hypothetical device that's fundamental to the theory of computation, assumes an infinitely long tape for reading and writing data. This assumption allows us to explore the boundaries of what is computationally possible. Lastly, let's not forget the field of mathematics itself, where infinity is not just a concept, but a tool. It's used in calculus to deal with limits, in set theory to understand the different sizes of infinities, and in geometry to describe points at infinity, aiding in simplifying equations and proofs. Infinity, in its many forms, continues to challenge our understanding of the universe. Infinity, countable or uncountable, is a concept that stretches our imagination to its limits. In our journey through the endless expanse of infinity, we've encountered some fascinating ideas. We've learned that not all infinities are created equal. Some are countable, like the set of natural numbers, while others, like the real numbers, are uncountable. The concept of countable infinity is akin to a hotel with an infinite number of rooms, always having space for one more guest. This is the incredible paradox of Hilberts Hotel, where even an infinite number of guests can always find room for one more. It's a concept that defies our everyday intuition, but in the realm of infinity, it's business as usual. Then, we explored the intriguing concept of uncountable infinity, an infinity so vast that it can't be matched one-to-one with the natural numbers. The real numbers between 0 and 1, for instance, are uncountable. We proved this using Cantor's diagonal argument, a proof as elegant as it is mind-bending. These concepts of infinity have profound implications. They challenge our understanding of the universe, forcing us to rethink our notions of space, time, and existence. They show us that infinity is not just a concept, but a fundamental part of our reality. Throughout our exploration, we've seen that infinity is much more than an abstract mathematical concept. It's a tool that allows us to grapple with the vastness of the universe and the infinite possibilities it holds. It's a testament to the power of human imagination and our ability to transcend the limits of our own understanding. So the next time you think about infinity, remember, it's more than just a never-ending story. It's a key that unlocks the door to unimaginable possibilities, a concept that expands our understanding of the universe, and a testament to the boundless potential of human thought. Infinity, in all its forms, is truly a concept without limits,